336. We will do a brief review of the test of hypothesis that we just finished. So the first thing is, what is hypothesis testing? Basically, the first question out of this is we don't know about population, because if we really want to know population, we need to do a census, okay, to get everything out of the population and examine it and to see what's going on. But we know it is very expensive to do a census. On the other hand, even if you do a census, it may not be so perfect, as you may know. When you do census, the data may be changing, at the same time. So let us say if you want to do a census, say how many people in our society in this country, but after you done the census, some people may die, right? And some people may be born. So in this case, you will hardly get the exact number. So the first important thing is because we have no idea about population, so therefore we have to be satisfied ourselves with the data from sample. But when we get the data from sample, it's only a portion of the population. So we need to make sure that it really reflects what's going on in terms of the population. That's the reason we have to do a test on this. So basically we have two tests, okay? One is called H0. One is called H1, okay? This is called null hypothesis. Basically, we will assume things as it is. So sometimes we can say this is status quo. The true meaning of status quo is called status quo antibalance. Status quo means, okay, the original situation, okay, the original situation. Anti-balance, anti means before. Balance means war, okay? So oftentimes we just say status quo, okay, status quo. Status quo means the original condition. But the original meaning for that is status quo anti-balance, okay? Of course, we may have examined, what's going on in terms of production, sales, whatever, and we get a number, okay? Then we say, well, this is probably what it is, okay? But of course, after we take a sample out of the population, we may figure out, well, there may be something wrong. So for the status quo, it is in the null hypothesis, okay, in the null hypothesis. But sometimes we may suspect something wrong there, okay? We may suspect there is something wrong there. Then we say that would be the alternative. And that is the way we test it, okay? Okay, then so let us get at one example. So the Consumer Association of Taiwan, they have done a survey on the weight of French fries. Probably you have consumed very much of the French fries. As you know, sometimes the salesperson, they are not very careful in putting the French fries into the bag, right? Sometimes you get more, sometimes you get less, but oftentimes you get less, okay? So there are some people, they say, maybe they write a letter to the Consumer Association, say, there's something wrong there. So they disguise, okay? Some of the people from the Consumer Association, okay, or Consumer Protection Association, they disguise, okay, they pretend they are consumers, but actually they are not. They want to inspect, whether they get enough French fries to people, okay? And so after a while, McDonald's, Wendy's, all these fast food restaurants, they claim that, let us say it is 500 grams, okay? Let us say they claim, okay, we indeed give customers 500 grams of French fries, okay? But of course, it may not be the case. So these people, they pretend they are consumers, but actually they are the people from Consumer Protection Association. They inspect that and find out, okay, this is what the company claims, right? But we are suspicious. We don't believe them, okay? And so they get there and to get French fries themselves, and then they expect it and find out, well, it's probably, let us say, 480, okay? So let us say the sample they get, okay? They get there several times and they, weight the French fries and figure out that it is only 480 grams. So is it enough? Okay. So in this case, whether we want to believe McDonald's, okay, or believe the Consumer Protection Association, we need to test it. We know sometimes we may make mistake. If it is due to a random mistake, that's acceptable, right? But suppose they purposely put too little in the bag, that is something wrong, right? They try to cheat customers. If that is the case, that's not acceptable. So something may be wrong. So in this case, we want to test it, okay? If indeed it is too small, then we say McDonald's made a mistake, okay? They made a false claim, okay? They say the French fries has 500 grams, but actually it is not. So basically, first you have to say, okay, what's our situation? We want to test, right? But we are facing this situation is that we have a product, okay, and the company claims the product has certain weight, okay? It weighs 500 grams. But at this point, we don't know whether that's true or not. So we take some sample out of the production, okay? We get orders of French fries and we try to figure out what's going on there. So the null hypothesis, we assume it is 500, right? And in this case, okay, now we want to be careful here. We don't worry about too much, right? If they give us more, no one's going to complain, right? More is better. So in this case, we are only concerned it may be too small, right? This is our concern. So if we say, this is our concern, we want to figure out whether it's too little or not, right? And so in this case, we say, this is our concern. And we say, we talked about this before, that H0 and H1 should be mutually exclusive, right? If they are mutually exclusive, then this should be greater than or equal to. So in any case, just ask yourself, before you're going to set the null hypothesis or alternative hypothesis, you want to ask yourself, what's your worry, okay? We worry about this product is too little, right? They don't have enough weight. If that is the case, you should put that into alternative hypothesis. And I gave you an example about elevator, right? So in terms of elevators, we only worry about there are too many people. It's too heavy that the elevator will not be able to carry those people. So if that is the case, we worry about too much, okay? So basically, we have three kinds of testing. One is this one, right? This is called left-hand test, okay, left-hand test. Or left-hand side test, okay? Because we want to make sure that it is not too little, not too small, whatever. And this one, we worry there is too much or too big, okay? And the other one is that, okay, so in this case, if you still remember the question in the midterm, right, 750 kgs, we worry about, the elevator maybe carrying too many people or too much weight, okay? And sometimes we just don't like, okay, in terms of medicine, right, we say medicine can kill cells, okay? And they can kill good cells, they can kill bad cells. But of course we want the medicine to kill bad cells, but unfortunately they are all cells, right? So in this case, too much medicine is not good, too little is not effective. Okay, so sometimes we worry about whether they are equal to or not, right? So let us say it's this. And this is a two-tail test, okay? In this case, this is two-tail test, okay? The case is like this, okay? If it is too small, then it's not equal to. If it's too big, it's not equal to either, okay? And in this case, if this is the number you get, so let us say you have to compare with one critical value in this case. So let us say the critical value is here. And if this critical value, let us say, is 490, right? If it is 490, so what happened? Because this number is smaller than this number, right? Smaller than the critical value. So what would you do? So you have two actions. First is this action, it is called A0. And then you have another action that's A1, okay? For A0, what does that mean? Because if the value is higher than this critical value, so we say, well, maybe there is a probability, okay? It is still the same thing with this, but we believe, okay? But we believe, it is H0 is true. So that means, okay, in this case, because the number is not that small, okay? It is not that small. So it is bigger than we can accept, bigger than this critical value. So still we accept that the mean, okay, of your product is greater than or equal to 500. But when it is too small, in this case, say 480, right? It is smaller than this one. So what kind of action should you take? You need to take action A1. What does A1 mean? You believe that actually the product is underweight, okay? So it is actually smaller than the company claim, okay? The same thing here, okay? You get another critical value. If it is very big, let us say it is here, right? If it is very big, then you're gonna believe it is too much, okay, or too big. And if it is not that big, okay, so let us say 750, right? So let us say this is 750, and let us say the critical value is 760. Okay, the critical value is 760. So if the value you found out, okay, x bar 0 is equal to 759, even though it is very close to this critical value, it's still smaller than this one, right? It's still smaller than this one, so what would you do? You're gonna do this, okay? You take action A0. And what does A0 mean? We believe that it is smaller than this number, okay? But let us say if it is x bar 0 is 760.1, okay? Even it is just greater than this number by 0.1, what would you do? You're gonna say, well, I'm going to take action A1. And what does A1 mean? You believe this is true, okay? The same thing here, too big, too small, okay? So basically 336, okay, if you got a book, or should I put it down on the blackboard? The first one is to get these two things set up, okay? The first thing is you get H0, H1, okay? You want to make a decision what kind of null hypothesis, alternative hypothesis you should take there, okay? So first one, you have to set up this. And then the second one, you want to determine your significance level, okay? Oftentimes, we use alpha, right? Alpha is equal to 0.5, okay? Or alpha is equal to 0.01. Or sometimes we say alpha is equal to 0.10. It all depends, okay? It all depends. It's up to you. But generally, you want to make sure that the probability of this error is small, right? You want to make sure this probability, this kind of error has a low probability. But we mentioned that before, right? This is what we call type 1 error, right? If type 1 error is small, what happened to type 2 error? Type 2 error will be big, okay? So in this case, sometimes you want to make sure that type 1 error is small, but as you know, when this one is smaller than beta, that's type 2 error, will be bigger, okay? So you want to be careful here. Anyway, the third one, identify the test statistic. So sometimes we use mean, right? Sometimes we use mean. Sometimes we use variance, okay? Sometimes we use standard deviation. But in this class, we never talk about standard deviation. So you have two things to worry about. One is mean, the other is variance, okay? So identify what is the statistics. If it is mean, okay, if it is mean, then it is easy, right? So you use x bar, right? Sometimes there's one variable, x bar. Sometimes there are two variables, then you have x bar, y bar, right? Okay? And again, so if you have one variable, then you worry about whether, first you have to make a decision, C, whether that's a Z distribution, right? Or T distribution. Under what kind of circumstances you're going to use Z distribution? The first thing is the population has to be normal, right? Population has to be normal, or you have a large sample. Okay, you have a large sample. Say the population is normal and also you have a large sample, then what do you use? You use Z distribution. But then let us say the population is normal distribution, but the sample size is small. So let us say it's 25, right, 26. What kind of distribution you're going to use? You're going to use T distribution. And when you use T distribution, you have to be careful because in this case, there is a degrees of freedom, right? Degrees of freedom. Oftentimes we use DF, okay, degrees of freedom to denote the degrees of freedom. And degrees of freedom for T distribution, so let us say we have n sample, right? Suppose we have n samples, what about degrees of freedom? How much should that be? How much is it? It is n minus 1, right? It is n minus 1, okay? And basically, let me go over again some of the things we need to know. But anyway, let us finish this first, okay? And then step 4, you have to set up a decision rule. The decision rule is very simple, right? You want to check the sample value, okay? In this case, sample, mean, sample, variance, whatever. You get from there and see if that value exceeds the critical value, okay? You want to compare this value, okay, with this value, okay? The sample value and the critical value. If this one, it depends on the situation, right? If you want to figure out whether that's too big or not, if this one is bigger than this one, then you say, yes, it's too big, right? If you want to compare whether it's too small or not, then if this one is smaller than this one, then you say, yes, it is too small. So you, in both cases, you're going to reject null hypothesis, reject H0, accept H1. But let us say it is within the limit, okay? Within this critical value, then what would you do? You accept H0, or you say fail to reject H1, okay? And of course, that would be generally the procedure you're going to follow, okay? Then sometimes you want to compare variance, right? If you want to compare, you want to figure out what's going on in the variance, then what would you do? What's the estimator? The estimator will be Sx squared, right? Xx squared. And let us say you want to estimate, okay, or want to test hypothesis of this variance. What kind of distribution should you use? Which distribution? It should be chi-square, right? Chi-square distribution, okay? And for chi-square distribution, the same thing. You have degrees of freedom, right? If the sample size is n, what about the degrees of freedom? It is equal to n minus 1, right? Okay? And then the next case will be we deal with two variants, okay? So sigma x squared, sigma y squared, right? In this case, okay, you're dealing with two variants, and then you want to use F distribution, okay? In this case, you're going to use F distribution. I believe we have finished this, is that right? Have we talked about this before? Let me briefly give you the formula, okay? So if you want to estimate this, generally when we do this, okay, we are trying to figure out whether sigma x squared is equal to sigma y squared. When we do this, okay, we try to figure out whether sigma x squared is equal to sigma y squared. And when we do this, okay, when we do this kind of test, in what kind of circumstances we're going to believe they are equal to each other, okay? So there's a value there, okay? So let's get to basically, if we want to do this, first thing we talk about the interval estimate, okay? The interval estimate. It will be less than or equal to Sx squared divided by xy squared. And here it will be F nx minus 1, degrees of freedom 1, and ny minus 1, and 1 minus alpha over 2, okay? And this is the right-hand side. It is xs squared divided by xy squared and divided by the F distribution with nx minus 1, ny minus 1 degrees of freedom, and the probability here, okay, is 1 minus alpha over 2. And here is the same thing. If you still remember, right, when we talk about sigma x squared, the interval estimate for that is equal to Sx squared, right? N minus 1. Okay? And then what is here? Here it is, okay, chi-squared n minus 1, 1 minus alpha over 2. Okay? And here, m minus 1 again, sx squared, chi-squared, m minus 1 alpha over 2. Okay? So basically, these are the last two distributions we talk about, and it is a little bit difficult in this way because it's kind of complicated. But in terms of formula, really, if you can figure out this one, okay, then basically that will be just the same thing. Okay. Okay, so now let us try to figure out, because we want to know whether they are equal to each other or not, right? This is what we want to figure out, okay? So let us say, after we've done the test, we figure out, we get a sample, right? And from the sample, we calculate the value there. This is what we get, okay? Sigma x squared divided by sigma y squared is between 0.9 and 0.5. Can this number be negative? Can this number be negative? Never, right? Because this is a positive number. This is also a positive number, so it will never be negative. And let us say after we get the sample and we figure out that this is the value of the, this is the interval estimate for this value, okay? And this is what we get. So the question is, under these kind of circumstances, is sigma x squared equal to sigma y squared? If they are not equal to, then which one is larger? Okay? So we have two questions here. The first question we want to answer is whether these two are equal to each other or not. Okay? And the second one, if they are not equal to, then which one is larger? So in this case, because sigma x squared and sigma y squared within this interval, right? It is within this interval. So what does that mean? Does this value include 1? This value does not include 1, because if this one is equal to this one, what does that mean? That means sigma x squared divided by sigma y squared has to be equal to 1, right? And does this value cover 1? No, it doesn't. So that means within the confidence interval we talk about, are they equal to each other? No. They are different from each other. Which one is larger? Sigma x squared or sigma y squared? Which one is larger? Because this value is smaller than 1, right? So which one should be larger? Sigma y squared should be larger, okay? And let us try to get another example, okay? So this is the first example. Then the second example say, okay, this is 1.9, this is 1.5, right? Okay, let us say it's this. Again, does this value cover 1? It doesn't cover 1, right? Because if this value has, if these two things are equal to each other, it should be equal to 1, right? And this value within the confidence interval, we know that they are not equal to 1. They are actually larger than 1, right? So the same thing here. We know these two things are not equal to each other. And in this case, which one is larger? Sigma x squared is larger, right? Okay. Okay, then we get to the third case. Okay, the third case, let us say it is 1.9 there, and this is 0.5 here. Okay, 1.9 there, 0.5 here. Okay. In this case, does this value cover 1? It covers 1, right? But is it exactly equal to 1? No, it's not. Because we say this is a probability, right? If there is a chance, okay, if there's a chance that this value covers 1, what does that mean? That means within this confidence interval, we can say they probably equal to each other, okay? So whenever you talk about probability, right, statistics, it is about probability. We cannot say for sure they are equal to each other because it's not this. It is 1.9 and 0.5. So we can only say within this confidence interval, we can say they are equal to each other, okay? Let's take a break. After we briefly review chi-square distribution, F distribution, there are some points that we need to clarify. So let us get to chi-square distribution again. Chi-square distribution has some interesting properties. So that is, we know if z squared, if we have standard normal and square it, we know that is chi-square distribution with degrees of freedom 1, right? And we know t distribution when the degrees of freedom, okay, gets to infinity. It gets to z distribution, right? So we also know that t distribution with degrees of freedom and square that, it is also chi-square distribution with degrees of freedom 1. And u, let us say, is chi-square distribution with degrees of freedom v1. And v is chi-square distribution with degrees of freedom v2. Then u plus v will be chi-square distribution with v1 plus v2, right? Okay, then we want to deal with this formula, okay? This formula here, so let me keep this here, okay? Okay, so how to denote a chi-square distribution? So P, okay, let us say this is a, so in this case, this is a random variable, okay? This is a random variable. And we say, if this one is greater than this one, alpha over 2, what does that mean? That means the probability should be alpha over 2, okay? So basically, the situation is here. We mentioned this before. So this is actually chi-square distribution. Let us say degrees of freedom n minus 1, alpha over 2. This kind of notation means that for the value up to from this value up, the probability is alpha over 2, right? So in this case, chi-square distribution, this random variable greater than this number, we know the probability should be alpha over 2. On the other hand, if it is less than it, right, less than, we know the probability should be 1 minus alpha over 2, okay? And so here you know, chi-square distribution, degrees of freedom n minus 1, 1 minus alpha over 2, okay? Then we have probability of a random variable, okay, is greater than or equal to chi-square distribution n minus 1, 1 minus alpha over 2. The probability is 1 minus alpha over 2, right? And then if it is less than that, it should be alpha over 2. So first you have to get familiar with these kind of notation, okay? Get familiar with this notation. Then the second step, we want to get to this formula, okay? Okay, so now we know n minus 1 times sx squared divided by sigma x squared, that is a chi-square distribution with degrees of freedom n minus 1, okay? So this is also what we know. We know z squared is a chi-square distribution with degrees of freedom 1, and we also know this, okay? This is what we know. I believe I proved this before, but anyway, so let us take that as granted, okay? Just believe me, okay? And then we want to develop the interval estimate for sigma x squared, okay? How to get there? Okay, we know P, and this is a chi-square distribution, right? Chi-square m minus 1, 1 minus alpha over 2 is greater than less than or equal to m minus 1 sx squared and sigma x squared less than or equal to chi-square m minus 1 alpha over 2. That is equal to 1 minus alpha, right? Because above this point, that is probability is alpha over 2. Below this point, the probability is also alpha over 2. So what's the probability within this area? It is 1 minus alpha, right? So I'm talking about a random variable. When the value is between this and that, okay, what should be the probability? The probability should be 1 minus alpha. So at this point, so far so good. Are you with me? So first we figure out what's the probability in this area, right? And then we want to figure out how to get from here to here, okay? We want to get the interval estimate for chi-square distribution. Any questions? Okay, now we want to manipulate this formula, okay? We want to manipulate it, okay? Okay, when we get this, so we get the reciprocal, okay? Reciprocal, remember? Reciprocal. So we put this upside down, downside up, okay? But you want to remember this is less than or equal to, right? So when we know 3 less than or equal to 4, less than or equal to 5, but when you put this upside down, right? 1/3 actually will be greater than or equal to 1/4 greater than or equal to 1/5. Okay, remember that? Okay, then this one, okay, will be, so actually this one will be smaller, okay, and when you put it into the denominator, so it should be here, okay, 1 over chi-square m minus 1 alpha over 2, right? And here you have it upside down, m minus 1 sx squared sigma x squared, right? And then you have 1 over chi-square m minus 1 minus alpha over 2, right? And still it is equal to 1 minus alpha, okay? And then it is easy, right? Because we're going to get here. We want to get this one to be 1, okay? We want to get the denominator to be equal to 1. If you want a denominator to be equal to 1, you have to time m minus 1 x squared to all sides, right? So then you have p m minus 1 sx squared chi-squared m minus 1 alpha over 2 sigma x squared okay, so that's the formula there, right? So if you want to estimate variance, this is the formula you will follow, okay? You'll follow this. Okay, and basically we know our chi-square distribution is related to F distribution. So let me give you the formula of F distribution and let us get from there and try to figure out here, okay? So, any questions? Okay, so we know what is F distribution. F distribution, we have 2 degrees of freedom, right? One is V1, V2. And what is that? That is chi-square distribution with V1 of degrees of freedom divided by V1, right? And then chi-square distribution V2 degrees of freedom divided by V2, right? So this is F distribution. Because of this, so we showed that before, f v1 v2 is actually equal to 1 over f v2 v1, okay? The same thing. You put it into a reciprocal, right? You get a reciprocal of that. This is what you get, okay? Any questions? Then we're going to start from here. Try to figure out what is that, okay? But let us try to use x and y. That would be easier. Let me see if that will be the case. Okay, here. Okay, so we know this is chi-square distribution, right? Okay, this is chi-square distribution. And let us say we have two things, nx minus 1 and ny minus 1, okay? Nx means the sample size of x. Ny means the sample size of y, okay? This is one variable. Nx is one variable. Ny is another variable, means the sample size, okay? And since we know it is like this, right? And we will try to figure out what's going on here, okay? Okay. So the numerator, it should be chi-square distribution nx minus 1, right? Okay? And this is the chi-square distribution. So actually, this is, let me put it this way, okay? nx minus 1 sx squared and sigma x squared, right? But this is only chi-square distribution because the second part is here, right? The second part you have to divide it by the degrees of freedom, okay? So then you have to divide it by nx minus 1, right? Okay, the same thing here. The same thing here, then you're going to have ny minus 1 sy squared sigma y squared divided by ny minus 1. Okay? Any questions so far? Okay, then what would you get? Because this one will cancel with this one, right? And this one cancel with this one. So what you get? You get sx squared divided by sigma x squared sy squared divided by sigma y squared. Okay? So then this will be equal to, let me see, sx squared sy squared and times sigma x squared sigma y squared. See if I get it right. Okay? So basically, it is like this, okay? So F distribution, the original definition is here, right? And then you can get from there to here and to here, okay? And so then we will go from here to get the estimation of sigma x squared and sigma y squared, okay? It may be a little bit complicated, but everyone follows me? And then the same thing we're going to discuss how to get a probability, okay? Have you done with this? Yes or no? Have anyone still need this part? Anyway, well, keep it here, okay? I'll keep it here. Then let us try to get to this part. The same thing. Probability of F distribution, right? This is the random variable greater than or equal to F nx minus 1 ny minus 1 alpha over 2. What is the probability? The probability is the same thing, is alpha over 2, okay? And so probability of F less than or equal to this, Because this is a continuous variable, right? This is a continuous random variable. So whether you put equal to or not, does it matter? It doesn't matter, okay? And this one, nx minus 1 and y minus 1 alpha over 2 is equal to what? 1 minus alpha over 2, right? And the same thing, we have p f greater than or equal to f nx minus 1 and y minus 1 and 1 minus alpha over 2. That will be 1 minus alpha over 2, right? And again, f less than or equal to f nx minus 1 and y minus 1 alpha over 2. That will be equal to, sorry. Right? Okay, so basically we got the same thing here. And now we want to derive the formula in this case. Okay, we want to derive the formula in this case. First we have to know how to denote the probability, right? And then the same thing, this is what we want to get. So we want to get this. And this is the F distribution. This is the variable, right? Okay, this is the variable. And the variable between these two values, okay, should be equal to 1 minus alpha. And what are these two values? These two values will be, okay, what is that? F. Because this is just a little bit too complicated. But anyway, let us stick to it, okay? Nx minus 1 and y minus 1. And this will be alpha over 2, right? And then here will be f, okay? Nx minus 1 and y minus 1 and 1 minus alpha over 2, okay? So basically, this is what we know in terms of the probability, right? And we say, now the same thing, okay? Let me draw a picture. But, you know, F distribution is not standard normal, but let me draw, anyway, something like this. So here you have f, nx minus 1 and y minus 1 and alpha over 2, right? And here you have f, nx minus 1 and y minus 1 and 1 minus alpha over 2. So this probability is equal to alpha over 2, and this probability is also equal to alpha over 2, right? So what's in between? In between it should be 1 minus alpha, right? So the same thing. I say we try to figure out the interval, right, for this. And the random variable, if it is between this value and that value, what should be the probability? The probability should be equal to 1 minus alpha, okay? Any questions so far? Okay, and what is this? We already know F distribution is here, right? This is F distribution, okay? F distribution is here. Okay? So let us put this number here. Okay? Okay. So then this is sx squared and sy squared times sigma y squared, sigma x squared, right? We just put this number in there, right? We just put this formula into this area because we know this is F distribution, okay, the random variable there. And f, x, nx minus 1 and y minus 1 alpha over 2. Okay, now we get into some difficulties because this is what we want, okay? This is what we want, but this is what we have, okay? So first thing, we want to make sure that this is on the upside and this on the downside, okay? So the same thing happened because this is A less than or equal to B less than or equal to C, right? And when we get a reciprocal of that, we should change the order, right? We should change the order, okay? So we have P 1 over F nx minus 1 ny minus 1 and alpha over 2, right? And then, because everything has to be upside down, so then this is xx squared sy squared, right? And then this is sigma y squared sigma x squared, right? And then this one should be down here, right? This one should be down here. So 1 over f nx minus 1 ny minus 1 and 1 minus alpha over 2. Okay? Any questions so far? Okay, because this is what we want, okay? This is what we want. So we have to get rid of this. If we want to get rid of this, how should we do it? Because the denominator is sx squared, the numerator is sy squared. So we have to multiply this and divide by this, right? So we have to multiply, because I've used blackboard, so let me do something easier, right? I can simply change this, okay? You multiply this, so what you get? You get sx squared, right? And then you have to divide it by this. So divide by sy squared. Then we get rid of this, because you get 1 here. And then the same thing there. You have sx squared divided by sy squared. Okay? So if you want to estimate the variance ratio, okay, the variance ratio of the population, what's the interval estimate? The interval estimate is exactly here, right? And the same thing as what we have derived, okay? And we say when you do this kind of interval estimate, actually what are you interested in? You are interested in whether sigma x squared is equal to sigma y squared, right? Whether they are equal to each other. And we mentioned that if this interval estimate, okay, if this interval estimate includes 1, if this value, okay, from here to here, if it includes 1, what does that mean? They should be equal to each other. But if this value does not include 1, what does that mean? They are not equal to each other, okay? So any questions? And F distribution will be used to test variance, okay? We will use it a lot of times, especially when we get to ANOVA, okay? Analysis of variance. Any questions so far from regarding chi-square distribution and F distribution? Okay, then we get back to the book. Okay, so let us try. Let us look at page 339, okay, page 339. In this case, they talk about 2 types of error, right? Type 1 error and type 2 error. Actually, we discussed this before. Just try to remind you again about type 2 error, type 1 error. So because it's based on probability, it's never certain that you are always right, okay? When you say you accept H naught, right? We know still, we don't know, I mean, exactly which one is true, right? H1 true or H not true. But because of the probability theory we have, we believe in H naught, right? But that means, of course, we may make a mistake, right? We may make a mistake. And so H1 may be true, H naught may be true, okay? H naught true, H1 true, If H naught is indeed true, and you believe you take action A naught, that means H naught is true. So you do a correct decision, right? If H naught is true, but somehow you reject H naught, then you made a mistake. This is type 1 error. And here the same thing, okay? You made a mistake because H1 is actually true, okay? But you take action A naught. You believe H naught is true, okay? You know, the question is, we don't know which one is true, okay? So that's the reason we have to do this kind of test. So when you do this kind of test, you have to be very careful. When this one is large, this one will be small. But when this one is small, this one will be large, okay? Okay. So basically, if there is only one variable, right, it will be easy. You just make a decision which one you're going to use, Z or T, right? When there are two variables, then it will be a little bit more difficult, okay? So let us say we are interested in mu x minus mu y, right? Okay? So in this case, you have to know the distribution of x bar minus y bar, right? Okay, and it is mu x minus mu y, okay? And the variance should be sigma x squared divided by nx plus sigma y squared divided by ny. Under what kind of circumstances will we use this one? If we use this one, what does that mean? X and y must be independent. Okay, if we use this formula, okay, for the variance, what does that mean? That means they are independent. And when we use this as the population variance, right, what should be our estimator for the population variance? Then it should be, okay, Sx squared divided by Nx plus Sy squared divided by Ny, okay? And then we mentioned that sometimes we know a little bit more information about the population. So let us say, okay, if we know sigma x squared is equal to sigma y squared, right? If we know this, then what happens? If we know this, then we should use SP squared, right? Remember, if we know these two things are equal to each other, then we should use SP squared. And what is SP squared? SP squared, okay, is equal to nx plus ny minus 2, nx minus 1